Um, in this video, we're going to prove that for all vectors v or elements v of a vector space capital V, the quantity -1 times v is equal to the additive inverse of v. So we'll ignore this for a second and we'll talk about something that we're probably used to seeing from the real numbers. That is something like -1 times let's say 3, and almost immediately you'll probably write this as -3, and this seems too obvious, so we generally think of -1, or at least I think used to think in high school and middle school and high school, -1 as being just a replacement for or a shorthand for the minus sign. While it's completely fine to treat it that way, it's really important to recognize that there is a proof. There's actually a formal proof behind this, and we're going to prove it for vector spaces, but it can be proved for the real numbers as well. Um, uh, the thing is, -1 times v and minus v, or the way we write it, this thing, -1 times v and minus v, are actually two different objects. They happen to be equal to each other, which is what we're going to prove in this video, but they are, strictly speaking, two different quantities, or at least definitionally, which happen to be equivalent. They happen to be equal to each other, but the way we think about it is slightly different, or different, yeah. -1 times v is the scalar multiplication of the scalar -1 with the vector v. Again, I am going to, like in the previous video about, uh, uh, I forgot what the previous video was about. It was about, yeah, proving that 0v is equal to v in for any vector v in the vector space v. I'm going to assume, just like in that video, that you're at least somewhat familiar with the idea of a vector space, assuming that you're studying linear algebra on the side, proof-based linear algebra on the side at least. And I am going to make a video on what vector spaces are, and or explain all the axioms and what they mean, and give some examples of vector spaces. And but that is going to be a topic of another video. But in this video, I'm going to assume you know what vector spaces and fields are, and you know you're somewhat familiar with all the properties. And I do have the properties listed out here. This is taken directly from Wikipedia, and so I do have all the axioms here for easy reference. But yeah, I'm familiar. I'm assuming you're familiar with scalar multiplication, addition, and terms like that. So -1 times v is the scalar multiplication of the field element -1, which is a scalar, with the vector v, which is a member of v. Meanwhile, -v, or minus v, however you want to call it, let's call it -v, is defined to be a vector v, and it's defined to be that vector v which, when added to v, gives you the additive identity 0. So we can really look at this definition over here in this axiom, inverse elements of vector addition. So for every element v, every vector v in v, there exists an element -v in v, called the additive inverse of v, such that v plus -v is equal to 0. So yeah, the additive inverse is a vector. Meanwhile, -1 times v is the scalar multiplication of the scalar -1 with the vector v. So in order to prove this, what we're going to do is start off with, essentially, we're going to um, uh, start off with supposing that, suppose v is any vector v, and we're going to say, we're going to start with the right hand side. Um, -v, then no, first we're going to use the definition of the additive inverse. So we can say, then we have, sorry for the awkward cut right there. My iPad battery almost died out, so I had to plug in the charger. So yeah, continuing with where we were. So we know -v is the additive inverse of v, the vector v. So we know that um, v plus -v, oops, let me rewrite that. V plus -v is defined to be equal to 0. So this is an axiom that every, like, -v is that number which, when added to v, gives you 0. Now 0 is something that we can right as being equal to 0 times v. And to see why, you might want to look at the previous video, or essentially you might want to look at the proof of the property that 0v is equal to 0, where 0 is a scalar and the 0 on the right is a vector, like it's a 0 vector v. So this was I already proved this property in a previous video. And so this is equal to 0 times v. So 0 here was a vector, now this is the scalar times v. Uh, and this scalar can be written as a sum of 1 and -1. So again, this is a familiar property of real numbers, that even real numbers, for every real number, there is an additive inverse, such that when they are both added, they give you the additive identity 0. So this is equal to 1 plus -1 of v. And now we use what is called the distributive property. So we use this second version, distributive of scalar multiplication with respect to field addition. So we have a plus b times v is equal to ab plus bv. So we can apply that over here. This is equal to 1v plus -1v. And we have this property here, which we call um, identity element of scalar multiplication. So 1 times v is defined to be equal to v. So 1 is the multiplicative identity. So we can replace 1 with just v. This is equal to v plus -1 times v. Great. So now that we've established this, we have that v plus negative v is equal to v plus negative v through a chain of equalities is equal to v plus -1v. So now you can probably guess what the next step is, but we're going to write it out formally. So now consider what I'm going to now. Okay, let me phrase it a different way. So we have that first we'll specify what we have achieved or what. So this is an intermediate hypothesis that is going to be used to prove our final result. So now we have that v plus -v is equal to v plus -1, the scalar -1 times v, adding the scalar the vector -v, which is the additive inverse of v, to both sides, we get -v plus, let me write it this way, plus v plus -v is equal to, this is going to be longer equality, so let me write it like this, -v plus v plus -1v. The reason I have the parentheses on v and plus -v is because that is the quantity that we're considering to be a single vector, because obviously two vectors add to give another vector in the same vector space. So that's another quantity that we're considering. Then we're adding -v to that quantity. So we're considering that we're adding this first and then adding -v to that. So, same reason that this has a parentheses around it. And now we're going to use associativity of addition, and we're going to immediately rewrite this as -v plus v plus -v is equal to -v plus v plus -1v. This becomes 0 obviously because of additive inverse. So we have 0 plus -v. By the way, v plus -v is equal to 0, but also -v plus v is equal to 0 because addition is commutative on over the vector space. So this is an axiom, by the way, and commutative vector addition. So that's cool. We have 0 plus -1, sorry, not -1v. We have 0 plus the additive inverse of v, which is -v, is equal to, again, 0, 0 plus -1 times the vector v. Now 0 plus anything is just that thing. So -v is equal to, again, 0 plus anything is that thing. So negative is equal to -v. If you notice, this is exactly what we want to show. So -v on the right hand side is equal to -1v on the left hand side, which so we have that same equality in reverse. So this is what was desired. So that is the end of our proof.